Hello, everyone. Welcome to Virtual Amsterdam. And is there a place for distributed storage in AI/ML on Kubernetes? I'm Diane Feddema. I'm a principal software engineer at Red Hat. And today I'm speaking with Kyle Bader, who's a principal software architect for cloud storage and data services at Red Hat. So next slide, please. So we want to know, is there a place for distributed storage for AI/ML workloads on Kubernetes? What do you think?
I would say yes, absolutely. And why were we interested in doing this? Well, there was, it kind of stemmed from a number of conversations that we had internally as we were, thinking about distributed storage and the implications of machine learning. And it kind of boils down to, many of you probably have an environment, well, if you're lucky, have an environment that looks maybe something kind of like this, right? And Kubernetes is awesome, so you've chosen to use Kubernetes to manage this environment. And most of the time there will be some number of general purpose compute nodes that are running your applications and your storage and so on and so forth. And then the lucky part is if you are able to have some special purpose compute with additional GPUs in order to kind of accelerate your machine learning workloads so that you can finish both training jobs and inference jobs a little bit more expeditiously. And collectively, this Kubernetes cluster that we're looking at here represents a fairly significant capital investment. So we want to make sure that it's used as efficiently as possible, right? We want to maximize our utility from this investment. So Kubernetes to the rescue, right? At a very simple level, right? Kubernetes is a scheduler. It does a lot of other things in addition to scheduling, but one of the things that it's here to help you with is packing bins. You can think of nodes as these bins, and instead of having dimensions like length and height and depth, those nodes have dimensions like amount of CPU, amount of memory, how much storage space do they have on their local storage devices, how much I/O can those storage devices handle, and we want to effectively fill these bins with pods, and we want to fill them as full as possible without them kind of impacting each other, in order to maximize the utility of that cluster. So we schedule a pod, and that pod is going to consume some amount of CPU, some memory. It will generate some amount of storage I/O and consume some amount of storage space. And if you draw this up onto this kind of multi-dimensional object here, you get a shape. And so each pod kind of has its own shape. And with all these different shapes of pods, you want to try to fill up the each of these dimensions as full as possible. So as you add another pod, right, represented here by this kind of dotted purple line, we want to we see that it's taking up an additional amount of CPU, additional amount of memory. It's going to consume some more storage I/O and take up some more storage space. Now, some of you might have noticed a problem here, and I'll kind of point it out, is that we've kind of exhausted the amount of CPU resources here. And what does that mean? Why is that bad, right? We want to maximize the usage of it, and so we want to use up all the CPU, don't we? Well, yes, we do, but we don't want to trap the other resources. Basically, we don't want to have this like stranded capacity in terms of memory and unused storage space and unused storage I/O. We want to use those. We want to use those efficiently as possible too. So one of the problems that you want to solve with the scheduler is to avoid trapped capacity. One way you can help avoid trapped capacity is by having fewer dimensions that are constraints. And so this is where distributed storage gets kind of interesting, because you can kind of abstract away storage. And then there are, because it's being remotely accessed, the the pods have ability to be scheduled in more places, and there's less constraints on scheduling them, such that it's easier to fill your bins maximally, and in turn maximize the utility of that significant capital investment. Now, the other time when distributed storage comes into the picture is when you need more storage space for a particular application than you have on any given node in your cluster, right? So if you need to if you have data that's larger than a node, then you're going to have to spread that data over multiple nodes. And guess what? Distributed storage helps you do that, right? So by kind of virtualizing the storage, kind of collecting a bunch of disks together, and then using various software-defined storage methodologies, it can kind of create this either virtualized block or file system storage or object storage, and then you can have larger data sets that a pod is interacting with than what you could get from any individual node. The other problem that might present itself is okay, you have available compute, right? And you want to use it up, but the data already exists on another pod, right? Because you're using local storage somewhere, and your data's over here. So now you're kind of sure, you could have something that's going to make that data over on the right host be remotely accessible, right? Maybe iSCSI or NFS or something to the node over on the left, but that running that NFS or iSCSI gateway is going to consume some amount, right? And so you can't kind of ad hoc provision it. And it would really just be better if we just kind of had a distributed storage system that was in place and gave you more flexibility gave Kubernetes more flexibility in terms of scheduling. So this is, and this is not, none of this is unique to Kubernetes or machine learning workloads. But it does apply equally to machine learning workloads, and so it was kind of in this thinking, this context that we started to ask the questions about distributed storage and machine learning. So a very simplistic, right, kind of truncated version of the machine learning lifecycle. Right now, of course, there's going to be something on the left that's the applications. Or sensors or whatever that's generating the data, and then there's more on the right, like training is not the end all be all, right? You're going to have to take that model and wire it into an intelligent application and do something useful with it, shopping cart, suggested products, or detecting fraud, or so on and so forth. But for the purposes of this discussion here, we've kind of simplified it to, okay, so there's the time to value is something that we want to shrink, and some of the things that need to be performed before we can realize value from that data is we're probably going to have to prepare it, wrangle it together in some sort of way, and then without distributed storage, we're going to have to move the data. So if it's going to take a really long time to run it on the general purpose compute, and it was processed on the general purpose compute, then we're going to have to move it to the special purpose compute in order to finish it in any sort of reasonable time frame. And then finally, once the data is there, then we can actually start training the model against that data. And then once it's completed, we're kind of onto the next phases of the life cycle. So with distributed storage, can we compress this? Can we compress and have get to that value faster? Can we reduce the time that it takes to get to that value? And if you implement kind of some sort of distributed storage, you could potentially kind of compress the data moving and model training into the same space, and perhaps that does mean that it inflates the time that the actual model training takes, but you potentially save yourself that data moving stage. Now, of course, an astute reader might go, oh, okay, well, if the data is not remote and the GPU node is accessing over to the network, isn't it kind of like the data is moving? And the answer is yes, right? So it's going to be kind of over the course of the model training, it's kind of incrementally, or either incrementally over the course of the whole training, it's grabbing some of the data it needs to keep the GPUs busy, or it kind of bulk loads it in the beginning and then processes it from there, right? So yeah, this is what we want, right? We want to see if we can compress that time to value by kind of collapsing these two stages by using remote storage and accessing the data in situ, right, in some sort of distributed file system, or object store or something like that. So the other interesting thing that comes about with distributed storage is it helps a lot with parallelism, right? And just kind of simple explanation of parallelism. Many of you already know all this, but if I'm digging a ditch and I'm alone and I break it up into 6 work units, it's going to take me longer, right? If I want to dig that ditch faster, I can recruit 2 of my best friends that are equally hard workers as me, and we'll each complete 2 units of work, and that ditch will be dug faster, right? And that's great. And the reduction in time that it takes to dig that ditch is speed up, right? And it's kind of the computer sciencey, what they call that is speed up. So can we additionally, in addition to kind of collapsing those two, the compute stage and or the training stage and the data moving stage, could we also affect speed up to further reduce the training time, potentially compensating for or going to further than we would be able to otherwise? So if we have this model training and collapsed model training and data moving step, can we parallelize? Can we add additional GPU hosts? Of course, this would be after we've stuffed as many GPUs as NVIDIA has engineered to be able to fit into a single system. But once you've exhausted the ability to scale up, you're only left with the ability to scale out. So if we scale out, can we further reduce the amount of time that it takes to do this kind of collapsed data moving model training step? So it's in like with this in mind, like this is the overall kind of like theory level thinking behind the question about is there a place for distributed storage for AI and ML in Kubernetes, right? So next we kind of needed to test this hypothesis, and so without further ado, I'll let Diane talk a little bit about a benchmark that we used for some testing called MLPerf.
Kyle, next slide, please. Okay, so as Kyle said, we're going to run an experiment, and we need models to train for this experiment, and we're going to train them with data that's sitting on distributed storage and then compare that to data that's sitting on local storage and see how each of them do. And so we decided to choose the MLPerf training benchmarks to run, and MLPerf is like an emerging industry standard for a standard benchmark that is designed to be used as a level playing field for comparing machine learning infrastructure. There are all these companies that are shown here that are contributors to MLPerf, and university researchers as well. So we thought this would be a great choice of a real-world benchmark that tests the entire system to run in our distributed storage experiment. Next slide, please. So the MLPerf benchmarks solve real-world problems, as I said, such as computer vision problems like identifying images, identifying objects in images, and translating one language to another. So we are going to run the SSD benchmark, which consists of a model. This SSD with ResNet 34, and uses the COCO Data Set, which is an a publicly available data set. So then we also are going to run the transformer model, and that uses the WMT public data set. So I'll talk a little bit about each data set, and all the code that we used here is open source. You can go to MLPerf.org and see the code that we ran. And also we're running MLPerf version 0.6 training in our experiments. Next slide, please. So this is an example of object detection and segmentation. And you can see that the objects have been detected and they've been labeled, and then the segmentation has happened also on the guy in the bicycle. So these sorts of applications use things like the COCO Data Set, which we're using, and each year there are competitions to improve the state of the art in this object detection and segmentation. So we just ran one of these benchmarks. Next slide, please. A little bit about the COCO data set that we used. It's the common object in context data set, and it has over 300,000 images. It allows researchers and people who are doing benchmarks like we are to take real-world problems of finding these objects in these scenes and outlining them and labeling them and seeing how your model does at that, seeing the accuracy level that you achieve. So the data set was created by Cornell in a joint project with Microsoft originally. And if you'd like to check out the data set online, next slide, please. You can download it, and you can also peruse around the data set and search for things like, in this case, you can submit queries on the COCO Explorer where you want to see all the scenes with horses and bicycles and cars, all the images, or whatever combination of the objects it recognizes. You can choose them here and just check the data set for if it's got the sort of objects that you are looking to recognize in your images. Next slide, please. So Kyle talked a bit about why we want GPUs. We want to get that speed up that Kyle was talking about. And in these benchmarks, we use neural networks that rely heavily on linear algebra, things like matrix multiply, dot product, things like that. And GPUs are extremely efficient at doing that matrix math. They're great number crunchers for matrix math. And so you can get thousands of times speed up. It's not unusual to say get a 3,000 times speed up if you run like a large matrix multiply on a GPU instead of a CPU. So what we're trying to do here is use these GPUs to reduce the training time, make those matrix operations go faster. And we also have to feed those GPUs with data, and that's what we're testing. Are we getting the data from this distributed file system there fast enough to keep the GPUs busy? So training times can take days or weeks, and if you made a slight error in your code and then you figure that out a week later, then your turnaround time, the work time for the data scientist or the researcher is not reasonable. So we want to shrink down that time to train so that you can iterate more, make more changes, improve your model quicker. Next slide, please. In MLPerf, we will be using Python. There are many languages that you can use, Lisp, R, Java. You could choose other languages to write a neural network application, but the benchmarks that we are going to be running use Python, and there's a good reason why many data scientists prefer Python, and it's because you have access to libraries, and I'm just listing 4 here that are very useful when writing neural networks. So There's Theano, TensorFlow, Keras, and PyTorch. And today in our example, we'll be using PyTorch. Another really nice thing about using Python is that in your Python code, you not only have access, in our case, to the PyTorch library, but you also have access to NumPy, and you can move these multi-dimensional arrays back and forth between NumPy and PyTorch very easily. The API is very easy to work with, and I think that's why researchers and programmers like it so much. Next slide, please. So just a little bit more about PyTorch. It's open source. It was created by Facebook. It was initially intended as a replacement for NumPy that used GPUs. NumPy doesn't. NumPy runs on CPUs. PyTorch runs on GPUs. With just minor modifications to your code, you can make your multidimensional arrays in NumPy run on GPUs when you're using PyTorch. So PyTorch was created so that it was easier to build neural networks. It uses something called tensors, which are really just multi-dimensional arrays, imperative multi-dimensional arrays that run on GPUs. And by imperative, I mean that when you execute, as you go down through your code, and you execute a line that uses a tensor, the computation is performed immediately when you hit that line of code. And not all implementations are like that. The first release of TensorFlow was not imperative. They have now switched to the imperative model because it's so popular, and in TensorFlow 2.0, they also use the imperative computation approach. So in PyTorch, you can run on CPUs or GPUs. You can switch back and forth easily with some minor changes in your code. And you get the benefit of slight changes to your code allow you to get huge speedups by using GPUs instead. Next slide, please. So when we were preparing our benchmarks to run on the cluster that we created, the Kubernetes cluster that we created in AWS, we first containerized the MLPerf benchmark, and we created a Docker file for it. And in our Docker file, we used NVIDIA's version of PyTorch. We built it from source. Then we added the scripts that ran the MLPerf benchmark, and we created that container image, pushed it to Quay.io, which has a repository, online repository, and then we pulled it into AWS when we actually ran this job on our cluster. And I'll show you the YAML next that we used to pull that image. Next slide, please. So this is actually a different image that we're pulling, but not in this case, we were pulling a CUDA vector add, but in our case, we pull the image for the MLPerf benchmark. But what I'm showing here is that you have some YAML that Kubernetes interprets and schedules you onto the correct worker node based on the resources you're asking for. So here I'm asking for 4 GPUs, which is what we had in our cluster in AWS, and Kubernetes and OpenShift will schedule that pod onto a node that has the GPU.
So what do we see? What happened when the rubber hit the pavement? How did this turn out? So before I ever talk about what we see, we like to give just splash up some details about the environment so that if people want to recreate this sort of work, they can do so. We have kind of the laundry list of versioning on the left there. We used OpenShift Container Platform 4.5, which maps to Kube 1.18, and then we used OpenShift Container Storage 4.4, which gave us Ceph Nautilus and Rook and Ceph CSI all kind of neatly packaged together. And then the cluster itself was just a few modest master nodes, and then we had some 3 pretty modestly sized dedicated storage workers that we use taints and tolerations to ensure that only the storage workloads were running on them. They had a couple SSDs each, and then the workers are relatively not particularly relevant here because all of the workload that we were running, or the one workload that we were running, was basically the different PyTorch MLPerf tests, and those had those GPU constraints and so that made sure that they were scheduled to the P38XL that we had provisioned, which has 4 of the NVIDIA V100s that each have 16 gigs of memory each. We used EC2 to run our cluster, US West 2 region, and then we spread both the compute and the masters, storage, and the worker nodes across different availability zones for fault tolerance. But of course, because we only had one GPU worker, it was in a single availability zone.
So the first benchmark that we ran is an object detection benchmark called SSD. And you can see here that you can see the software stack that we ran. We, just like Kyle described a minute ago. And so we're using Python and PyTorch and CUDA. And on top of that, we're running OpenShift. And and of course, Red Hat CoreOS is the operating system that we're running. And you can see that we have a training time where the data was sitting on local SSD. So when we say local SSD, we mean on the same worker node where the V100 GPUs are. And so we had a time of 45 minutes, 92 seconds. It's 0.92 minutes, actually. And then we had training time using Ceph of 45.78 minutes. So you can see there's essentially no difference here. The difference is definitely noise at this point. We could have run it again and it could have been faster with Ceph. So that was an excellent outcome, and it shows that, yes, it's reasonable to use distributed storage for these training benchmarks. Next slide, please.
That's good news, right? We're not completely crazy.
Right, that's great news.
So what was the other one that we ran? It was
So we ran the translation benchmark, which translates from German to English and English to German. And so this is a natural language processing benchmark. And it was only about a 4% difference here in our timings, slightly over 4.01%, I think. So again, we put the training data on the local node and tested it, and got a timing of 62.91 minutes. And then to compare side by side, we put the training data in Ceph and got a timing of 65.43 minutes. So again, this was a great experiment, and we got a good result. So we were happy about that.
Yeah, it's interesting. I mean, they're so close, right? When you said 4% variance or something, it's like if we ran each of these 20 times, would it just be like in the error bars, right? It wouldn't even. It's effectively indifferent. And so we kind of go, okay, well, this was interesting. Why did it come out this way? So we wanted to dig in a little bit to Prometheus, right? Look at some of the telemetry from the test to really try to understand what's going on here. Why do we see what we saw?
And so it's very handy and useful to use Prometheus and Grafana together in Kubernetes and OpenShift. And right here, we're looking at our transformer run. And you can see that along the top there, the top row graph is GPU utilization, and it goes from 0 to nearly 100% when the job starts at 9:55. You can see the time along the x-axis there. And so we are just keeping these GPUs very busy for the duration of that run. And you can see that in Ceph there are, and also actually next row down is the graph for the memory utilization, and we're at about 15 gigabytes of GPU memory used for the duration of the job. So, and then the Ceph IO ops are kind of distributed equally across the entire run and are pretty low. Not really hitting the storage that hard. So, Kyle, would you like to say any more about this?
Yeah, it was kind of like we would launch this this particular workload, and I was sitting there looking at the storage cluster. I'm going, it's like, is it working? I was like, this Ceph is bored, right? Like we're not doing anything. And I think the I/O that we're mapping here is the data operations, right? So there might be some additional like file system, stats and listings and stuff that are going on here that are increasing the I/O a little bit. But for the most part, these are relatively, it's reading like a sentence, right? We're like, well, those I/O sizes must be really small. Like if you divide the number of I/Os by the amount of data that's coming out over the particular periods. So and then we're like, well, it's probably just reading like a sentence, and then it's converting the sentence, and then doing a comparison type thing. So it's a relatively, at least for this workload, it's not a particularly storage intensive machine learning workload.
Right, and it trains on sentence pairs. So those, like the English sentence and the German sentence, are sent together, and then you train. That's how the model is trained to translate from one to the other. And so, yeah, it's not particularly I/O intensive, and the I/O is human language sentence pairs sent together. So, we look at the next
one. Was actually it was more interesting, I thought, because it was totally different, right, than what we saw with the transformer, right? This was the single, what is it? Single
stage detector.
Single stage detector. Yeah.
It's object detection.
So my favorite, because it's the SSD, right? And being a storage guy, we love things that we love SSDs, right? So the SSD workload was also overloaded terminology, but it was interesting from a storage perspective because it basically just bulk loaded everything at the very beginning, and then once it was over to the GPUs, then it Ceph was just kind of relaxing while we burned up a bunch of energy crunching and doing this image detection. So that was kind of interesting. We saw a lot more I/O, but it was concentrated in like a brief, almost two minute window.